Welcome to Little English Studio, the channel where science, history, and human curiosity come alive in clear and beautiful English. Today we journey into the fundamental laws of the universe, to the moment when physicists discovered that nature, long thought to be perfectly balanced, hides a subtle asymmetry. This is the story of breaking nature's symmetry, a revelation that reshaped our understanding of matter, antimatter, and the origin of the universe. Join me as we explore the experiments, the scientists, the principles of symmetry and violation, and the profound implications for physics, cosmology, and the very nature of reality. For centuries, the laws of physics appeared perfectly symmetric. The equations governing motion, energy, and forces seemed indifferent to direction, left and right, matter and antimatter, past and future. This symmetry suggested a universe that was balanced, elegant, and predictable. Yet in the mid-20th century, experiments in nuclear physics began to reveal cracks in this assumption. In 1956, theoretical physicists Tsung-Dao Lee and Chen-Ning Yang proposed that one type of symmetry, known as parity, might not be conserved in weak nuclear interactions. Parity symmetry implies that the mirror image of a physical process should behave identically to the original. In other words, nature should not distinguish left from right. This assumption had gone largely untested in weak interactions, the forces responsible for processes such as beta decay, the emission of electrons from radioactive nuclei. Until then, physicists assumed parity conservation as a fundamental law. Experimental verification became essential. In 1957, Qin-Xiang Wu, a brilliant experimental physicist working at the National Bureau of Standards in the United States, designed a groundbreaking experiment to test this principle, using cobalt-60, a radioactive isotope that undergoes beta decay. Wu cooled the cobalt to near absolute zero, aligned the nuclear spins with a strong magnetic field, and measured the direction of emitted electrons. Her experimental setup was meticulous, requiring extreme precision to detect the tiny asymmetry in electron emission. The results were astonishing. The electrons preferentially emitted in a direction opposite to the nuclear spin, demonstrating that parity was violated. Nature indeed distinguishes left from right in weak interactions. The experiment confirmed Li and Yang's prediction and shattered the long-standing assumption of universal symmetry. The implications were profound. Symmetry, once thought to be a guiding principle of all physical laws, was no longer absolute. The discovery opened new avenues in particle physics, leading to deeper understanding of the weak force, neutrinos, and the structure of fundamental particles. Breaking symmetry also had cosmological consequences. The apparent dominance of matter over antimatter in the universe might be linked to subtle asymmetries in the laws of physics. If matter and antimatter behaved identically, the universe would contain equal amounts of both and annihilate into radiation. Yet we exist in a universe dominated by matter, suggesting that the laws of nature themselves are slightly biased. The violation of parity was only the beginning. Later discoveries of CP violation, the combination of charge conjugation and parity, showed that even the combined mirror image and particle-antiparticle symmetries are not absolute. Experiments with neutral kaons in the 1960s revealed that these particles decay differently than their antiparticles, confirming that nature exhibits subtle but essential asymmetries. The theoretical framework of the Standard Model of particle physics incorporated these violations, accounting for weak interactions and the observed behavior of fundamental particles. Yet the questions remained. Why does the universe favor matter over antimatter? What determines the degree of asymmetry? Ongoing experiments with B-mesons, neutrinos, and other particles continue to probe these mysteries. Breaking symmetry also influenced other areas of physics. Condensed matter systems, superconductivity, and phase transitions often rely on symmetry principles and their violations. Understanding symmetry breaking allows physicists to predict the emergence of new phenomena, patterns, and forces. The conceptual lesson extends beyond physics. Symmetry and its breaking reflect the subtle complexity of nature. A universe that is orderly yet not perfectly balanced, predictable yet full of surprises. Scientists like Wu, Li, and Yang exemplify the courage to challenge assumptions, to design precise experiments, and to interpret results that contradict conventional wisdom. The narrative of breaking symmetry is also a human story of creativity, collaboration, and perseverance in the pursuit of knowledge. Their work was recognized with the Nobel Prize in Physics for Li and Yang in 1957, while Wu's contribution, though critical, reminds us of the historical inequities faced by women in science today. symmetry breaking remains a central theme in modern physics. From the Higgs mechanism, which gives particles mass, to ongoing searches for CP violation in neutrinos, the principle informs theories of the early universe inflation and the fundamental laws that govern reality. It teaches us that nature is not always intuitive, that apparent balance may hide hidden biases, and that discovering these asymmetries can illuminate the deepest structures of the cosmos. Visualizing the experiment, one can imagine cobalt nuclei at near absolute zero, spinning in unison, electrons erupting preferentially in one direction, a subtle but decisive twist in the fabric of the universe. The elegance lies not only in the mathematics, but in the experimental ingenuity required to reveal it. Breaking nature's symmetry is a testament to the interplay of theory and experiment, of prediction and observation, a moment when human curiosity penetrated the veil of the universe, revealing that even the fundamental laws are richer, more intricate, and more mysterious than anyone had imagined. The legacy of this discovery continues to inspire physicists and thinkers, showing that questioning assumptions and probing the unseen can yield revelations that reshape our understanding of reality. It invites us to see the universe not as perfectly fair and mirrored, but as a dynamic, evolving system, full of surprises and subtle biases, that these asymmetries give rise to complexity, life, and the very existence of the cosmos as we know it. And that was our journey into breaking nature's symmetry, the discovery that the universe is not perfectly balanced, and that fundamental laws can favor one direction, particle, or process over another. If you enjoyed this exploration of physics, discovery, and the hidden intricacies of the cosmos, please like this video. Leave a comment telling us what fascinated you most about symmetry violation. And subscribe to Little English Studio for more cinematic stories told in clear and beautiful English. Until next time, keep exploring, stay curious, and remember that even in a universe that seems orderly, surprises await those who look closely.